Welcome to this lesson on IPv6 addressing. In today's increasingly connected world, understanding IPv6 is crucial for managing modern networks. This lesson will provide an overview of why IPv6 was developed, how it differs from IPv4, and its key features. Now, IPv6 was designed to address the limitations of IPv4 and support the growing demands of the Internet, including scalability, security, and simplified configuration. Let's dive into the topics we'll cover in this lesson. So we'll cover why IPv6. We'll also cover the differences between IPv4 and IPv6, how IPv4 is different from IPv6 and the structure and types of IPv6 addresses. We'll also cover how IPv6 simplifies network configuration, its key benefits such as enhanced security and better support for real-time data delivery. By the end of this lesson, you'll have a solid understanding of IPv6 and its role in modern networking. So let's get started. Okay, and we'll start with why use IPv6. To understand the importance of IPv6, let's first examine the challenges faced by IPv4. And the first challenge is that IPv4 uses a 32-bit address space, providing only about 4.3 billion unique addresses. With the exponential growth of the Internet and IoT devices, IPv4 addresses have become limited or scarce. Organizations often use NAT or network address translation to map multiple private IPs to a single public IP, but NAT introduces complexity and limits functionality. Another challenge is routing table growth. The current IPv4 routing infrastructure is a matrix of flat and hierarchical routing, leading to large routing tables in backbone routers. IPv6 addresses this issue by supporting efficient hierarchical addressing, reducing the size of routing tables, and so on. One more challenge is need for simpler configuration. IPv4 often requires manual configuration or DHCP to address assignments, while IPv6 introduces stateless address autoconfiguration or SLAC, enabling devices to automatically configure themselves without relying on a DHCP server. One more challenge is IP layer security. While IPv4 supports optional IPsec, it's not mandatory. IPv6 mandates IPsec, ensuring secure communication over public networks, and better support for real-time data. IPv4 type of service or TOS field has limited functionality for quality of service or QoS, while IPv6 improves QoS with dedicated fields for traffic classification and flow labeling, enhancing real-time data delivery. Now, IPv6 uses a 128-bit address space, providing approximately 340 undecillion unique addresses, enough to assign an IP address to every atom in the surface of the Earth. Now, let's compare IPv4 and IPv6 to highlight their key differences. And we start with IP address spaces here. So IPv4 has got 32-bit or 4.3 billion addresses, while IPv6 has got 128-bit or 340 undecillion addresses. Then address format. IPv4 has got dotted decimal address format, that is, for example, 192.168.1.1, while IPv6 has got hexadecimal address format, for example, 2001:ODB8::1. As for header complexity, IPv4 has got variable length header, while IPv6 has got fixed length simpler headers. Then auto-configuration. IPv4 requires DHCP or manual setup, while IPv6 supports SLAAC or stateless address auto-configuration. As for security, IPv4 hasn't got mandatory security. It has got optional IPsec, while IPv6 requires mandatory IPsec. Then routing efficiency. For IPv4 it's flat and hierarchical routing, while for IPv6 it's hierarchical routing. And multicast and anycast. It's limited support for IPv4 and native support for IPv6. So IPv6's larger address space and improved features make it ideal for modern networks, especially with the rise of IoT and mobile devices. Now let's switch to the understanding IPv6 addresses. So IPv6 addresses are represented in hexadecimal format, separated by colons. Here is an example of an IPv6 address. You can see it on my screen. To simplify, IPv6 supports zero compression, allowing consecutive zeros to be replaced with double colons. For example, as you can see on my screen, here we've got several zeros and we can replace them with double colons. Now, IPv6 addresses are derived into two parts. That is, network prefix, which identifies the network segment similar to IPv4 subnetting, and interface identifier, which identifies the specific device on the network. Now, IPv6 addresses are globally routable, eliminating the need for NAT and enabling true end-to-end connectivity. Now, what are the types of IPv6 addresses? IPv6 defines several types of addresses to meet different networking needs. And the first type is unicast. It identifies a single interface, for example, 2001:db8::1, and it's used for one-to-one communication. Another type is multicast. It identifies a group of interfaces. For instance, FF02::1 for all nodes on the local link. And it's used for one-to-many communications. Then we've got anycast. It's assigned to multiple interfaces, but packets are delivered to the nearest interface based on routing metrics. It's used for load balancing and redundancy. Then we've got link local. It's automatically assigned to interfaces, for instance, FE80::1, and it's used for local network communication. Then we've got global unicast. These are publicly routable addresses, equivalent to public IPv4 addresses. Now, every IPv6-enabled interface has at least one link local address, which is used for local network operations like neighbor discovery. Now, let's take a look at IPv6 auto-configuration options. One of IPv6's standout features is its ability to simplify network configuration through auto-configuration. And first option is SLAAC, or Stateless Address Auto-Configuration. Devices generate their own IPv6 addresses using the router's prefix and their MAC address. And here no DHCP server is required, making deployment easier. Then we've got IPv6 DHCP IPv6. It's similar to DHCP in IPv4, but DHCP v6 provides additional configuration options like DNS servers. And manual configuration. Administrators can manually assign static IPv6 addresses for specific devices. Now, SLAC is ideal for small networks, while DHCP-v6 is better suited for enterprise environments that require centralized control. Let's take a look at the benefits of IPv6. So here are the key benefits of IPv6, and the first benefit is its scalability. So the massive address space ensures no risk of address exhaustion. The next benefit is its efficient routing. Hierarchical addressing reduces the size of routing tables. Another one is its enhanced security. It's mandatory IPsec security, which ensures secure communication. Improved QoS. Dedicated fields for traffic classification and flow labeling enhance real-time data delivery. And plug-and-play networking. SLAC enables automatic address configuration without manual intervention. So IPv6 is not just an upgrade, it's a fundamental redesign of the Internet protocol to meet the demands of the future. Okay, great job, you've now learned the basics of IPv6 addressing, including why it's needed, how it differs from IPv4, and its key features. These concepts lay the foundation for understanding how IPv6 works and how to integrate it into your networks. The next lesson will be the introduction to IPv4 and IPv6 differences. Welcome back. In this lesson on the differences between IPv4 and IPv6, we'll try to understand these differences, why they are crucial for managing modern infrastructure. So IPv6 was designed to address the limitations of IPv4 and introduce improvements that make networking more efficient, scalable, and secure. So IPv6 isn't just an upgrade, it's a fundamental redesign of the Internet protocol to meet the demands of today's connected world. Let's explore the key differences between IPv4 and IPv6, focusing on their structure, functionality, and features. And we'll start with address space. One of the most significant differences between IPv6 and IPv4 is the address space. So as for IPv4, here it uses a 32-bit address space, providing approximately 4.3 billion unique addresses. The limited address space has led to issues like IP address exhaustion and the widespread use of NAT or network address translation. While IPv6 uses a 128-bit address space, offering about 340 undecillion unique addresses. This vast address space eliminates the need for NAT and ensures that every device can have a globally routable IP address. The next difference is in auto-configuration. Another major improvement of IPv6 is auto-configuration. Now, IPv4 requires manual configuration, as you know, or DHCP, to assign IP addresses. This can be cumbersome in large networks with many devices. While IPv6 supports stateless address auto-configuration or SLAC, enabling devices to automatically configure their own IP addresses using the router's prefix and their MAC address. So DHCP version 6 is also available for environments requiring centralized control. So SLAC simplifies network deployment, especially in IoT and mobile environments where devices frequently join and leave the network. The next difference is in simplified header format. The header format in IPv6 is simpler and more efficient compared to IPv4. So IPv4 has a variable length header with optional fields, making packet processing slower and more complex, while IPv6 uses a fixed length header with fewer fields, reducing processing overhead. Optional features are handled through extension headers, improving flexibility without complicating the core protocol. So the streamlined IPv6 header improves routing efficiency and reduces latency. The next difference is in multicast and quality of service. IPv6 introduces significant improvements in multicast and quality of service. So for IPv4, multicast is optional and not widely supported, while in IPv6, multicast is included as native support, reducing broadcast traffic and improving efficiency. As for flow labeling, IPv6 introduces a flow label field in the header, enabling true QoS by identifying and prioritizing specific traffic flows. This ensures better support for real-time applications like video conferencing and VoIP. So flow labeling in IPv6 allows routers to prioritize traffic based on predefined rules, enhancing user experience. The next difference is in built-in security. Security is a core feature of IPv6. In IPv4, IPsec is optional and often implemented using proprietary solutions. Security is not inherently built into the protocol, while in IPv6, IPsec is mandatory, ensuring secure communication at the IP level. This provides encryption and authentication by default, protecting data from eavesdropping and tampering. So mandatory IPsec in IPv6 makes it easier to implement end-to-end security across networks. The next difference is elimination of NAT. IPv6 eliminates the need of NAT or network address translation. So in IPv4, NAT is commonly used to map multiple private IPs to a single public IP, conserving address space. However, NAT introduces complexity and breaks certain protocols. While in IPv6, with its massive address space, the need of NAT is eliminated. Devices can communicate directly over the internet, simplifying network design and improving performance. So removing NAT enables true end-to-end connectivity, which is essential for modern applications. The next difference is in DNS and address resolution. IPv6 introduces changes to DNS and address resolution. So IPv4 uses A records in DNS to map host names to IPv4 addresses. It relies on ARP or Address Resolution Protocol to resolve IP addresses to MAC addresses, while IPv6 uses Quad A records, so that'll be 4A in DNS to map host names to IPv6 addresses. It replaces ARP with Neighbor Discovery Protocol or NDP, which uses multicast to resolve addresses. So NDP in IPv6 is more efficient than ARP in IPv4, as it operates as the network layer and supports additional features like router discovery. And finally, packet size requirements. IPv6 imposes stricter requirements for packet size, while IPv4, here it must support a minimum packet size of 576 bytes, possibly fragmented. Fragmentation is performed by both routers and the sending host. But in IPv6, the required minimum of packet size is 1280 bytes without fragmentation. Fragmentation is performed only by the sending host, reducing router overhead. So here we've got small packet and here we've got large packet. Larger packets or packet size in IPv6 improve performance and reduce the need for fragmentation. Great, you've now learned the key differences between IPv4 and IPv6, including the address space, autoconfiguration, header format, multicast routing, security, and DNS integration. These improvements make IPv6 a more scalable, efficient, and secure protocol for modern networks. Next up, we'll have an overview lesson of IPv6 addressing. I'll see you there. Welcome back to this lesson on IPv6 addressing. So IPv6 is the next generation of Internet protocol designed to address the limitations of IPv4 and support the growing demands of modern networks. One of the most distinguishing features of IPv6 is its use of much larger addresses, that is 128-bit compared to IPv4's 32 bits. So IPv6 addresses are expressed in hexadecimal format, making them easier to work with for subnetting and calculations compared to IPv4's decimal notations. In this lesson, we'll explore how IPv6 addresses are structured, how to convert binary IPv6 addresses to hexadecimal, and how to simplify these addresses using zero compression. So let's dive in. So IPv6 addresses are 128 bits long, divided into 8 groups of 16 bits each. Each group is represented by 4 hexadecimal characters, separated by colons. Take a look at this example on my screen. This might seem complex at first, but don't worry. IPv6 includes features like zero suppression and zero compression to simplify the notation. Now, as you remember, IPv6 provides approximately 340 undecillion unique addresses, ensuring there is no risk of address exhaustion. So as you can see, this address is separated into several groups. Group 1 is this 2001, Group 2, 0db8, and so on. Now, what's hexadecimal numbering system? Before dividing into groups, let's dive into IPv6 address conversion. Let's briefly review the hexadecimal numbering system. Hexadecimal base 16 uses 16 unique symbols. So these are numbers 0 through 9 and letters A through F, representing values 10 through 15. For example, the decimal number 16 is written as 10 in hexadecimal format, and the binary number 1111 is written as F in hexadecimal. So 4 ones is written as F. And understanding the system is key to converting IPv6 addresses from binary to hexadecimal. Now, you can use, of course, the calculator application in Windows Server to convert between binary, decimal, and hexadecimal formats. So let's walk through the process of converting a binary IPv6 address to hexadecimal. Here is an example binary IPv6 address. So we've got lots of numbers here. So if we split this 182-bit address into 8 blocks of 16 bits, we can then convert each block to hexadecimal. So this first block here can be converted to 2001, here it is, and so on. Then we can combine the results and write the hexadecimal values separated by colons. So let's go ahead and convert the first block, for example. As you can see, all this long binary line can be converted to this 4 digits hexadecimal value. And we can do this for each block here. Now, IPv6 addresses can be simplified using zero suppression and zero compression. Zero suppression is when you remove leading zeros within each block. So as you can see on my example here, we remove the zeros and get this final result, suppressed result. And zero compression is when we replace contiguous blocks of zeros with a double colon. So here in this address, as you can see, we've got contiguous blocks of zeros, so we can remove them and we get this final result after compression. So zero compression can only be used once per address to avoid ambiguity. Now let's walk through really fast on how the conversion process looks like using the calculator application in Windows Server. So you can open the calculator app and switch to programmer mode. Then select binary as the input format and enter a 16-bit binary block. So that will be step 3 here. Then switch to hexadecimal to see the result. And repeat for each block to build the full IPv6 address. So using tools like Calculator app simplifies manual conversions and ensures accuracy. Now again, some words about importance of IPv6 addressing. First off, it eliminates NAT, enabling true end-to-end connectivity. Its hierarchical structure improves routing efficiency. It supports auto address configuration or SLAC, simplifying network deployment. And it integrates mandatory security features like IPsec. Great, you've now learned the basics of IPv6 addressing, including how to convert binary addresses to hexadecimal, simplify addresses using zero compression, and why IPv6 is essential for modern networks. These skills lay the foundation for working with IPv6 in real-world environment. Next up, we'll take a look at the introduction to IPv6 address structure. I'll see you there. Welcome back to this lesson on the structure of IPv6 addresses. So understanding how IPv6 addresses are organized is crucial for managing modern networks. In this lesson, we'll explore the components of an IPv6 address, including the prefix, subnet ID, and interface identifier. We'll also discuss the different types of IPv6 addresses and their purposes. So IPv6 addresses are 128 bits long and are divided into two main parts, as you remember. The network portion, that is prefix, and the host portion, that is interface identifier. So let's dive into the details of IPv6 address structure and its components. So what are IPv6 address components? Each IPv6 address consists of 128 bits divided into two main sections. That is prefix, that is network portion, and its 64 bits which represent the network portion of the address. This includes the global route and prefix and the subnet ID. The global route and prefix identifies the organization or ISP, while the subnet ID allows for internal subnetting within the organization. And interface identifier, that is host portion, it's the remaining 64 bits which uniquely identify the host of the network. By default, the interface identifier is often derived from the device's MAC address or generated randomly. Now, unlike IPv4, IPv6 always uses a /64 prefix for unicast addresses assigned to hosts, ensuring consistency across networks. So, what type of IPv6 addresses do we have? IPv6 supports three main types of addresses, each serving a specific purpose. First off, unicast addresses. They identify a single interface. Packets sent to a unicast address are delivered to one specific device. Examples include global unicast, that is publicly routable, and link local, that is local subnet communication. Then we've got multicast IP addresses. Multicast IP addresses identify multiple interfaces. Packets sent to a multicast address are derived to all devices in the group. Multicast replaces IPv4's broadcast functionality. And finally, any cast IP addresses, they identify multiple interfaces but delivers packets to the nearest device based on routing metrics, useful for load balancing and redundancy. Now, IPv6 does not use broadcast addresses. Instead, it relies on multicast addresses for one-to-many communication. So what is global unicast addresses? Global unicast addresses are the IPv6 equivalent for public IPv4 addresses. They are globally routable and reachable over the internet. The structure of global unicast addresses is as follows. The first 3 bits are fixed as 001, making global unicast addresses start with 2 or 3. Like you see on my screen, the example which starts with 2, that is 2001. Then the components of global unicast addresses are as follows. Global routing prefix. It identifies the organization or ISP. Then subnet ID. It allows for subnetting within the organization. And interface ID identifies the specific device. So global unicast addresses provide a vast pool of unique addresses, solving the exhaustion problem faced by IPv4. Another type of IP addresses is unique local addresses. Unique local addresses are the IPv6 equivalent of IPv4 private addresses. They are routable within an organization but not on the internet. The purpose of such addresses is as follows. They are used for internal communication within a private network, and it prevents address conflicts when managing networks. The structure of such addresses is as follows. It starts with the prefix FC00:7. So the most common range is FD00:8. Here you can see an example of such a prefix. Now, the organization identifier is unique local address, which is randomly generated, reducing the risk of duplicate address spaces. Another type of IP addresses is link local addresses. Every IPv6 enabled interface automatically generates a link local address for communication within the local subnet. The purpose used for essential tasks like neighbor discovery, equivalent to ARP in IPv4 and DHCP v6 communication. They are non-routable and limited to the local link. Its structure is as follows. Always starts with the prefix FE80:/64. So link local addresses are essential for IPv6 operation and are automatically assigned even if no other address is configured. And there are also special IPv6 addresses. IPv6 includes several special addresses for specific purposes. These are unspecified address, written as : that is all zeros used to indicate the absence of an address. Loopback address, that is written as : 1 used for testing communication on the same device. And compatibility addresses which help facilitate the transition from IPv4 to IPv6. Examples include IPv4 mapped IPv6 addresses. These special addresses ensure smooth operation and compatibility in IPv6 networks. And zone IDs for link local addresses. When a device has multiple network interfaces, each interface may reuse the same link local address. To distinguish between them, IPv6 uses zone IDs. The format for zone IDs is as follows: address %zone_ID. For example, this one on my screen, here we've got this %3, meaning that it's a zone ID. The purpose for such zone IDs for linked local addresses is to help identify which interface is being used for communication. Now, Windows-based systems use the interface index as zone ID, making it easy to identify the correct interface. Okay, great job. You've now learned about the structure of IPv6 addresses, including their components, types, and special addresses. These concepts are foundational for understanding how IPv6 works and how to implement it in real-world networks. Next up, we'll take a look at the introduction to IPv6 autoconfiguration. See you there. Welcome back to this lesson on IPv6 autoconfiguration. One of the standout features of IPv6 is its ability to configure itself automatically, reducing the need for manual intervention or complex configuration protocols. This makes IPv6 networks easier to deploy and manage. Now, IPv6 supports both stateless and stateful autoconfiguration, allowing flexibility in how devices obtain their addresses and other network settings. In this lesson, we'll explore the types of autoconfiguration, how they work, and the states of IPv6 address passes through during the autoconfiguration process. So let's get started. And we'll start with stateless autoconfiguration slide. The first type of IPv6 autoconfiguration is stateless autoconfiguration. This method allows devices to configure themselves without trying on a centralized server like DHCP v6. So how it works? First, a host generates a linked local address automatically for each interface. Then the host listens for the router advertisement or RA messages from routers to the local network. The RA messages include the network prefix which the host combines with its interface identifier to form a globally routable IPv6 address. The limitations of this process is as follows. Stateless autoconfiguration does not provide additional configuration options like DNS server address or domain names. So stateless autoconfiguration is ideal for simple networks where minimal configuration is required, such as IoT devices or small branch offices. Then we've got stateful autoconfiguration. The second type of IPv6 autoconfiguration is stateful autoconfiguration, which relies on a DHCP version 6 server to assign IPv6 addresses and other configuration parameters. Let's take a look at how it works. So the host receives instructions from the router via router advertisement messages to use DHCP version 6. The host communicates with the DHCP version 6 server using multicast IPv6 addresses to obtain an IPv6 address, DNS server addresses, domain name information, and other optional settings. So stateful autoconfiguration is ideal for enterprise environments where centralized control over IP address assignment and additional configuration options is necessary. And unlike IPv4, which uses broadcast messages for DHCP, IP version 6 uses multicast messages to communicate with DHCP version 6 servers. There is also combined autoconfiguration. In some cases, IP version 6 networks use a combination of stateless and stateful autoconfiguration. This hybrid approach provides best of both worlds. So how it works? The host uses router advertisement messages to obtain the network prefix and configure its IP version 6 address. Then the host also communicates with a DHCP version 6 server to obtain additional configuration options, such as DNS server addresses. The advantages of such approach that this approach simplifies address assignment while still providing centralized control over other network settings. So combining stateless and stateful auto-configuration ensures flexibility and scalability in large dynamic networks. Now let's take a look at auto-configured address states. During the auto-configuration process, an IPv6 address goes through several states that define its life cycle. Understanding these states helps troubleshoot issues and ensure proper address assignment. The first state is tentative state. So the address is being verified for uniqueness using the duplicate address detection or DAD algorithm. And it lasts until verification is complete, so the address cannot receive unicast traffic. Then valid state. The address has been verified as unique and can send and receive unicast traffic. Then preferred state. The address is fully operational and actively used for communication. Deprecated state. The address is still valid but discouraged for new communication. Existing connections may continue to use it. And invalid state, the address is no longer usable for sending and receiving traffic. Please note that the duplicate address detection process ensures that no two devices on the same network have the same IPv6 addresses, preventing conflicts. Now let's walk through a practical example of IPv6 auto-configuration. So for stateless auto-configuration, a device connects to the network and generates a link local address. Then it listens for router advertisement messages and combines the received network prefix with its interface identifier to form a global unicast address. And for stateful auto-configuration example, here the router instructs the device to contact a DHCP version 6 server. The device uses multicast messages to communicate with the DHCP version 6 server and obtains additional settings such as DNS server addresses. And finally, combined configuration example, here the device uses router advertisement messages for the network prefix and DHCP version 6 for DNS and other settings. So this hybrid approach is commonly used in enterprise networks to balance simplicity and centralized control. Okay, great job! You've now learned about the different auto-configuration options for IPv6 addresses, including stateless, stateful, and combined configurations. You also explored the life cycle of an IPv6 address during the auto-configuration process. Next up, we'll have a brief knowledge check quiz for correct to reinforce your knowledge on the information covered in previous lessons. I'll see you there. Now that we've covered the key concepts of IPv4 addressing and auto-configuration, let's test your understanding with a series of knowledge check questions. These questions will reinforce what you've learned and ensure you're ready to apply these concepts in real-world scenarios. So let's dive into the first question. And the question is, what is the primary purpose of stateless address auto-configuration, or SLAC, in IPv6? Is it to assign DNS server addresses dynamically? Option B, to allow devices to configure their own IPv6 addresses automatically. Option C, to replace the functionality of DHCP version 6. Or option D, to provide centralized control over IP address assignment. Here, think about how SLAC simplifies network configuration by enabling devices to generate their own IP version 6 addresses without relying on a DHCP server. So press pause here and think about the correct answer. And the correct answer here is option B, to allow devices to configure their own IPv6 addresses automatically. As you remember, Slack enables devices to automatically configure their IPv6 addresses using the router's prefix and their interface identifier, often derived from the MAC address. While Slack simplifies address assignment, it does not provide additional configuration options like DNS server addresses, which require DHCP version 6. So Slack is ideal for small networks where minimal configuration is needed, such as IO devices or branch offices. Let's move on to question 2. Which type of IPv6 address is used to for communication within the local subnet and is automatically assigned to every IPv6 enabled interface? Is it option A, global unicast address, B, unique local address, C, link local address, or D, anycast address? Here, recall the purpose of link local addresses and how they are essential for IPv6 operations, such as neighbor discovery and router advertisements. And the correct answer here is option C, link local address. So link local addresses, as you remember, are automatically assigned to every IPv6 enabled interface and are used for communication within the local subnet. They are non-routable and always start with prefix FE80::/64. Link local addresses are critical for essential IPv6 functions like Neighbor Discovery Protocol or NDP, which replaces ARP in IPv4. Let's carry on to question 3. What is the main difference between stateful and stateless autoconfiguration in IPv6? Is it option A, stateful requires a DHCP version C server, while stateless uses router advertisements only? B, stateless provides DNS server addresses, while stateful does not? C, stateful is used for global unicast addresses, while stateless is used for link local addresses? And D, stateless requires manual configuration, while stateful is automatic. Here, think about how stateful and stateless autoconfiguration differ in terms of how devices obtain their IPv6 addresses and additional configuration options. And the correct answer here is option A, stateful requires a DHCP version 6 server, while stateless uses router advertisements only. So, stateless autoconfiguration relies on router advertisements, or RA, to provide the network prefix, allowing devices to configure their own addresses, while stateful autoconfiguration uses a DHCP version 6 address and server to assign IPv6 addresses and other configuration options, such as DNS server addresses. So stateless autoconfiguration is simpler but lacks advanced options like DNS settings, which require DHCP version 6 in stateful mode. Question 4. Which of the following IPv6 addresses is equivalent to IPv4 loopback address, which is, as you remember, 127.0.0.1? Is it option A, 2 colons, option B, : 1, option C, FE80::1, or option D, FF02::1? Here, recall the special IP version 6 addresses and their purposes. The loopback address is used for testing communication on the same device. So here the correct answer will be option B, : 1. The IP version 6 loopback address is : 1, which serves the same purpose as the IP version 4 loopback address, which is 127.0.0.1. It allows a device to send packets to itself for testing and troubleshooting. Now, the loopback address is never assigned to a physical interface and is not routable. And we move on to question 5. What is the purpose of the 0 ID in an IPv6 link local address? Is it option A, to identify the network prefix, B, to distinguish between multiple interfaces on the same host, C, to assign DNS server addresses, or D, to enable multicast communication? Here consider how zone IDs help differentiate link local addresses when a device has multiple network interfaces. So the correct answer here will be option B, to distinguish between multiple interfaces on the same host. When a device has multiple network interfaces, each interface may reuse the same link local address. The zone ID, for example, FE80::1%3, helps identify which interface is being used for communication. Now, in Windows-based systems, as you remember, the zone ID corresponds to the interface index, making it easy to identify the correct interface. And finally, question 6. Which of the following is valid representation of the IPv6 addresses, or IPv6 address, here it is, using zero compression? So you'll need to apply zero compression to get a correct answer here. Is it option A, B, C, or D? Here, recall the rules for zero compression in IP version 6. Remember that the double colon can only be used once per address. And the correct answer here will be option A. So zero compression, as you remember, replaces contiguous blocks of zeros with a double colon. In this case, this address at the top is transformed to this address in option A. So zero compression simplifies IPv6 notation, but can only be used once per address to avoid ambiguity. Okay, great job completing this knowledge check. You've demonstrated a solid understanding of IPv6 addressing and auto-configuration. These concepts are foundational for managing modern networks and ensuring smooth integration of IPv6. Welcome to this lesson on configuring IPv6 settings. Understanding how to configure IPv6 addresses and related settings is essential for managing modern networks. In this lesson, we'll explore the various methods of assigning IPv6 addresses, including manual configuration, stateful auto-configuration, and stateless auto-configuration. We'll also cover the key options available in the IPv6 properties dialog box and advanced TCP/IP settings. Now, unlike IPv4, IPv6 is designed to support automatic configuration, making it easier to deploy and manage large-scale networks. So by the end of this lesson, you'll have a clear understanding of how to configure IPv6 settings to meet the needs of your network. So let's get started. So IPv6 introduces several methods for assigning addresses to network interfaces. These methods provide flexibility and simplify network management. And the first method is, of course, manual configuration. Administrators manually assign one or more IPv6 addresses to an interface. It's useful for servers and devices requiring static addresses. Then there is stateful DHCP-v6 method. It uses a DHCP version 6 server to assign IPv6 addresses and other parameters like DNS server addresses. It's ideal for enterprise environments that require centralized control. The next method is stateless auto-configuration. Here, devices automatically configure their own IPv6 addresses using router advertisement messages. It eliminates the need for a DHCP version 6 server in many cases. And combined configuration, it combines stateless auto-configuration for address assignment with DHCP version 6 for additional parameters like DNS. Now, a link local address is always automatically configured on every IPv6 enabled interface, regardless of the method used for other addresses. So when configuring IPv6 settings on a network interface, the General tab of the Internet Protocol version 6 TCP/IP version 6 properties dialog box provides several options. And the first option is obtain an IPv6 address automatically. It enables stateful or stateless auto-configuration, simplifies deployment by allowing devices to configure themselves. Then we can select use the following IPv6 address. It allows manual configuration of an IPv6 address and default gateway. It requires specifying the subnet prefix length. Typically it's /64. And we can also configure DNS server settings here. We can choose between obtaining DNS server addresses automatically or manually specifying them. Manual configuration is useful for ensuring consistent DNS resolution. For most networks, stateless auto-configuration is sufficient for address assignment, but DHCP version 6 may be needed for DNS and other parameters. Now, the Advanced TCP/IP Settings dialog box provides additional configuration options for IP version 6. Here we can specify multiple IPv6 addresses. We can add multiple unicast addresses for a single interface, and each address requires an IPv6 address and subnet prefix length. We can also set up multiple default gateways. We can configure multiple gateways for redundancy and specify whether the metric is manually set or determined by connection speed. As for route metrics, we can control the priority of routes based on metrics. It's useful for optimizing traffic flow in complex networks. So the ability to configure multiple addresses and gateways makes IPv6 highly flexible for diverse network environments. Now, if we switched in Advanced TCP/IP settings to DNS tab, the DNS tab allows you to define or fine-tune DNS-related settings. And here we can specify DNS addresses, we can list DNS servers in the order they should be required or queried. We can ensure reliable name resolution by prioritizing preferred servers. We can also specify DNS suffixes here. We can append primary and connection-specific DNS suffixes for resolving unqualified names. And we can specify custom suffixes for specific connections. And then we can set up dynamic DNS registration. We can register the connection's IP version 6 addresses in DNS and use connection's DNS suffix for additional registration. So dynamic DNS registration ensures that device names are always up to date in DNS, simplifying network management. Now let's take a look at the key differences between IPv6 and IPv4 address assignment. So let's compare IP version 4 and IP version 6 address assignment to highlight the differences. First off, automatic configuration. In IPv4, it's limited, a PIPA for local networks only, and in IPv6, it's built-in stateless auto-configuration. Then link local addresses. In IPv4, it's not mandatory, while in IPv6, it's automatically assigned. As for DNS configuration, in IPv4, it's typically manual or via DHCP, while in IP version 6, it can be automatic or manual. As for multi-homing, In IPv4, it's rarely used, but in IPv6, it's common. Interfaces often have multiple addresses. So IPv6 automatic configuration reduces the need for manual intervention, making it ideal for IoT and mobile devices. Great, you've now learned about the various methods of assigning IPv6 addresses, explored the configuration options in the IPv6 properties dialog box, and discovered advanced TCP/IP settings. These skills are essential for deploying and managing IPv6 networks effectively. Next up, we'll take a look at the tools for configuring IPv6 addresses. So see you there. Welcome back to this lesson on tools for configuring IPv6. While Windows Server can auto-configure IPv6 in most scenarios, advanced networking environments often require manual configuration. In this lesson, we'll explore the tools and methods available for configuring IPv6 settings, including graphical interface, PowerShell commandlets, and NetSH command line utility. So understanding these tools will empower you to configure IPv6 efficiently, whether you are managing a single server or automating tasks across multiple systems. By the end of this lesson, you'll be familiar with how to use these tools to assign IPv6 addresses, configure default gateways, and manage DNS settings. So let's get started. And we'll start with configuring IPv6 via GUI. The simplest way to configure IPv6 is through the graphical user interface. You can access IPv6 settings by opening the Internet Protocol version 6, TCP IPv6 properties dialog box from the Properties of a Network Interface in the Network Connections folder. So the steps are as follows. Open Network Connections folder, right-click the desired network interface and select Properties, select Internet Protocol version 6 and click Properties, and configure basic settings like IPv6 address, subnet, prefix length, default gateway, and DNS server addresses. So this method is ideal for quick one-off configurations, but may not scale well for large environments. And that's where PowerShell comes in handy. For more flexibility and automation, you can use Windows PowerShell commandlets to configure IPv6 settings. PowerShell provides a rich set of commandlets for managing IPv6 addresses, or default gateways and DNS servers. So the common commandlets are as follows. New net IP address, we can assign a new IPv6 address here. Then set net IP address, we can modify existing IPv6 address properties. Then set DNS client server address, we can configure DNS server addresses for an interface. Then get net adapter, we can list network adapters and their indexes with this commandlet. And get net IP addresses will display IP version 6 address information for a specific interface. So PowerShell commandlets are particularly useful for scripting repetitive tasks, making them a favorite among IT professionals. And as an example, to assign a global unicast IPv6 address with a prefix length of /64 and a default gateway, we type the following command. New net IP address, interface ls Ethernet, for example, IP address, we type the IP address here, prefix length 64, default way, and we type the default way here. Default gateway, sorry. And how do we verify IP version 6 configuration with PowerShell? After configuring IPv6, it's important to verify the results. You can use the get net IP address commandlet to display IP version 6 address information for a specific interface. So you type get net IP address, address family IPv6, where interface ls equals Ethernet, for example. And we'll get the following output. will get link local address, global unicast address, and address state. Is it tentative, preferred, or invalid? So the interface becomes multi-homed when it has both a link local and a global IPv6 address. Now, another way to configure IPv6 is using netsh command line utility. It's a powerful tool for configuring IPv6. So netsh allows you to configure IPv6 settings directly from the command line, making it ideal for scripting and remote management. And the common commands are as follows. To add an IPv6 address, we type netsh interface IPv6 add address local area connection, and then to add default gateway, we type netsh interface IPv6 add route. Then to add a DNS server, we type netsh interface IPv6 add DNS server. So use netsh when working in environments where PowerShell isn't available or when you need lightweight command line tools. Now let's compare the three tools for configuring IPv6. We've got GUI, PowerShell, and netsh. GUI is quick one-off configuration for quick one-off configurations. The advantages: it's easy to use and beginner friendly. PowerShell is for scripting and automation, it's flexible and integrates with workflows. While netsh is command line utility, it could be a bit outdated, but nevertheless it's good to know about this command line utility. It's lightweight and works remotely. So choose the tool that best fits your needs, whether it's simplicity, automation, or portability. Great, you've now learned about the tools available for configuring IPv6, including the GUI, PowerShell, commandlets, and netsh. These tools provide flexibility and scalability, allowing you to manage IPv6 settings efficiently in various environments. Next up, we'll take a look at few examples, practical hands-on examples performed in our test environment. So I'll see you in this demo lesson. Welcome back to this hands-on lesson on configuring IPv6 settings. We had 39 characters in this IP address, but after compression we've got only 11 characters left. Much easier to type and remember. These methods of assigning IPv6 addresses, including manual configuration, stateful autoconfiguration, and stateless autoconfiguration. We'll also walk through practical steps to configure IPv6 settings using both the graphical interface and command line tools like PowerShell and netsh. So unlike IPv4, IPv6 is designed to support automatic configuration, making it easier to deploy and manage large-scale networks. By the end of this lesson, you'll have a clear understanding how to configure IPv6 settings to meet the needs of your network. So let's get started. Now, I've logged into my lead SVR1 server in this test domain, which is learnedlessons.com, with lead NetBIOS name. And first, let's take a look at how to assign address for IP version 6. So again, as you remember from our previous lesson, IPv6 introduces several flexible methods for assigning addresses to network interfaces. And the first method is manual configuration. Administrators manually assign one or more IPv6 addresses to an interface. It's useful for servers and devices requiring static addresses. So let's walk through configuring IPv6 settings using a graphical user interface. For this, you'll need to open Network Connections folder and select the desired network adapter. You can do this by clicking on this item in the bottom right corner and select Network and Interface Settings here, and then select Change Adapter Options here. Or you can go to Server Manager, go to Local Server here, and select Ethernet adapter here, and click on this link. That will bring you to network connections as well. Another method to open network connections is to type ncpa.cpl and select control panel item from here. That will bring you to this network connections window as well. Then right-click the adapter and choose Properties. Or you can double-click the adapter and again choose Properties. Then select Internet Protocol version 6, here it is, and click Properties again. On the General tab, you can choose one of the following options. As you can see, the first option is to obtain an IPv6 address automatically that will enable stateful or stateless autoconfiguration. Or you can choose Use the following IPv6 address. It allows manual configuration for an IP version 6 address. You can configure subnet prefix length here, default gateway, and DNS server addresses. For manual configuration, you can enter IPv6 address, for example, 2001.2001:db, db 8:1:1. Then we can set the subnet prefix length, as you can see by default it's 64, and specify the default gateway. For instance, let's copy the same IP address and insert it here. But of course, as you know, this won't work. A device can't have the same IP as its gateway. This is just an example. If we want to have a more real-life configuration, let's add 0 here, that will be : 10. Subnet prefix will leave the same, 64, and default gateway will leave 1 here. As for DNS settings, we can set up primary DNS server here. In my case, as you remember, it's .22. So for IPv6 DNS configuration, that will be 2001:db8:22. We can specify our DHCP server that also runs DNS, or use a public IPv6 DNS as backup. So let's specify DHCP server here, for instance 20.01:db8:20. If we want an external DNS resolution, for instance a Google DNS resolution, let's change it to 20.01, and that'll be 4860:4860:48 here. So as you can see, we are using these double colons in every setting. As you remember, it's named zero compression, and it replaces consecutive groups of zeros in this full IP version 6 IP address. So before this compression, okay, let me press cancel here and demonstrate you how to perform the same actions with PowerShell. So for advanced users, PowerShell provides a powerful way to configure IPv6 settings. Let's configure an IPv6 address and default gateway using PowerShell. For this, we'll open PowerShell with administrative privileges. So I'll press Start here, and I can click on this PowerShell icon here. Or I can go to Server Manager, go to Tools, and select Windows PowerShell here. Let's make font a bit larger. So I'll go to Properties and select 36 here. Click OK. So after opening Windows PowerShell with administrative privileges, we can use a new net IP address command let to assign a new IPv6 address. So let's make our prompt a bit shorter like this and type the following: new -net IP address. Don't forget about tab auto completion here. Then we'll add a parameter interface ls. And as you remember, our interface ls is Ethernet. Here it is. You can check it with PowerShell as well. So interface ls will be in double quotes Ethernet, then one more parameter that will be IP address, and that will be 2001 colon db 8 colon let's say 10. So I'll type 10. Let's go to the next line with this tick here and add one more parameter that will be prefix length, which is 64, and one more parameter default gateway that'll be 2001 colon db8 colon 1. Let's hit return, and that will configure the settings we need. Now we can go ahead and verify this configuration. So let's type the following: get dash net IP address, and then we'll specify address family, that is IP version 6, with the following: where in curly braces we'll be looking for $underscore dot interface ls, which equals to, in double quotes, Ethernet. Let's hit return here, and we get the information. So if we scroll up a bit here, we'll find interface index here, that is %9. So as you remember, it's a zone ID, also called scope ID, and it's used with IP version 6 link local addresses in Windows servers. So it identifies which network interface to use for link local addresses, and it's required for link local addresses because they are not globally unique. And as you remember, it's also an interface index. Then we've got address family here, IP version 6. It's a unicast type IP address, prefix length 64. Now we've got IP address, and prefix origin is manual. So PowerShell is ideal for scripting repetitive tasks, making it a favorite among IT professionals. Now we can also configure IPv6 DNS servers with PowerShell. For this, let me type CLS to clear the screen, and we can use the following command: set dash DNS client server address, then interface index. As you remember, it was %9, or we could use interface alias, that is Ethernet in our case, in my case, and then provide the server address here, that is 2001 colon, and we have 10 missing here, so 2001 db8 colon 22. Hit return, and that'll set up our DNS server. We can also test DNS resolution with nslookup command, so we could type nslookup, for instance, learnedlessons.com for 2001 colon db8 colon 22. Hit return, and we get request timed out because we haven't set up IP address on our domain server, domain controller server. But that's how you check the connectivity and test DNS resolution. Another powerful tool to configure IPv6 is to use netsh command line utility. And here is how you can use it. Again, you open command prompt with administrative privileges, so you'll need to type cmd, open command prompt, and use net.netsh command here, then interface IPv6 add address, then Ethernet, and the address itself 20.1 colon db8 colon 10. The object already exists because we've just set it. Then we can add default gateway. Again, we'll type netsh interface IPv6 add, and instead of address we'll type route, then the route 2:0 Ethernet, and this time we'll leave just one here in the IPv6 address. Set it invalid prefix parameter 00 --0 because, colon 0, because we'll need to specify / here before 0. Hit return again. Object already exists because we've just set it with PowerShell. And we do the same for DNS server netsh interface IPv6 add, and then instead of this route we'll type DNS server for Ethernet adapter, and we'll make it colon 22. Hit return. Object already in the list. Now let's move on to some advanced TCP/IP settings. So let me get back to our network connections here. Go to Ethernet adapter, go to properties, go to Internet Protocol version 6, go to advanced here, and here in IP settings tab we can add multiple IPv6 addresses and specify subnet prefix length. So right now we've got only one. We can add one more here and specify its length. We can also configure multiple default gateways. So again, we'll need to click add and add one more default gateway. And then we can go to DNS tab here and specify DNS server addresses in order of priority. Right now we've got only one. We can add several more as well and append primary and connection specific DNS suffixes here. So we'll need to select this, append these DNS suffixes here and add the needed DNS suffix. And we can also enable dynamic DNS registration for connections. So we'll need to select these ticks here. So the DNS tab in IPv6 is similar to IPv4 but lacks WINS related features since IPv6 does not use NetBIOS. And again, we can check the settings in command prompt here. So let me go back to the PowerShell prompt, clear the screen, and you now know how to get net IP address configuration with net IP address family IPv6 parameter. Then we can use get-net route commandlet with address family parameter for IPv6. That'll reveal the routing information. And we can also use get-DNS client DNS, not this one, but DNS client not client, but DNS server. Again, DNS client server address address family IPv6. That'll reveal DNS configuration. And of course, we can use old but handy tools like, let me clear the screen here, like ipconfig command. So we type ipconfig /all. That will reveal all the IP configuration information. And by the way, to pin IPv6 address, you use pin, let me demonstrate it, pin-6, and then the IPv6 address. So you'll need to specify IPv6 address here to test IPv6 connectivity and to ensure the configuration is correct. Okay, you've now learned about the different methods of assigning IPv6 addresses, explored practical hands-on steps for configuring IPv6 settings using the GUI, PowerShell, and NetSH command line utility, and then verified the configuration. The skills are essential for deploying and managing IPv6 networks effectively. So I hope it was informative, and I'd like to thank you for viewing. Welcome back to this lesson on using DHCP-v6 in IPv6 networks. As organizations migrate from IPv4 to IPv6, it's essential to ensure the critical networking services like DHCP and DNS are configured to support the new protocols. In this lesson, we'll explore how DHCP v6 works in Windows Server 2016 and above. Of course, the latest is preferred 2012, Windows Server 2012, its configuration options, and how it integrates with IPv6 addressing. Sorry, I've said Windows 2000 Server 2012, but the latest is Windows 2025. So if you build your lab, it's preferred to build it with the latest Windows Server version, which is currently 2025. Now, while IPv6 supports automatic address configuration through stateless address autoconfiguration, which is SLAC, DHCP version 6 provides additional flexibility by assigning addresses and other parameters like DNS server information. By the end of this lesson, you'll understand how to configure DHCP v6 scopes, exclusions, and list durations, as well as how DNS integrates with IPv6 environments. So let's dive in. And we'll start with configuring DHCP for IPv6. When the DHCP service is installed on a computer running Windows 2016 Plus, the DHCP console displays two nodes, one for IPv4 and another for IPv6. This allows administrators to create and manage scopes for both protocols seamlessly. Options for configuring DHCP version 6 scope are as follows. First, we can create an IPv6 scope. It defines a range of IPv6 addresses to assign to clients. And here we can specify the subnet prefix and prefix length. For instance, 2002:db8:/64. The second option is to configure an IPv6 prefix and preference. You can configure preference to prioritize certain prefixes over others. The third option is to create exclusions. You can exclude specific IPv6 addresses from the scope to prevent conflicts with statically assigned addresses. And finally, configuring lease time. You can set the duration for which an IPv6 address is valid. Shorter lease time is often used for wireless devices, while longer leases are suitable for wired connections. Now, unlike IPv4, IPv6 DHCP servers can also assign prefixes to network segments, enabling hierarchical addressing. After creating an IPv6 scope, you can configure additional settings to enhance functionality. And these are the reservations. You can reserve specific IPv6 addresses for critical devices like servers or printers, which ensures coexistent addressing for these devices. And scope and server level options. So here you can configure options at the scope level, which applies to a specific subnet, or server level, which applies globally. The examples include DNS server addresses, domain names, and router advertisements. So use reservations for devices that require static IPv6 addresses but still benefit from DHCP version 6 for additional configuration options. Now, the DNS server in Windows Server 2016 and later versions fully supports IPv6, ensuring seamless integrations with IPv6 environments. Now, let's take a look at how DNS works with IPv6. First off, we've got this Quad A records. Computers with IPv6 addresses register themselves in DNS using this Quad A records, which maps host names to IPv6 addresses. Another feature is dynamic registration. Devices can dynamically register their IPv6 addresses in DNS. Alternatively, the DHCPv6 server can handle registration on behalf of clients. And of course, there are also static Quad A records. You can manually configure static Quad A records in the DNS console for devices that don't use dynamic registration. Now, proper DNS configuration ensures that IPv6 enabled devices can resolve names and communicate effectively across the network. And of course, don't forget about reverse lookup zones in IPv6. If your organization uses reverse lookup zones, you'll need to create separate zones for IPv4 and IPv6 addresses. And the process to set up reverse lookup zones for IPv6 is as follows. First, IPv6 reverse lookup zone itself. Here you create a reverse lookup zone using the ip6.arpa domain. And an example of such a zone you can see on my screen. Here it is. It's quite long example where the IPv6 address, which is, for instance, this one, the first one, 21:db8:1, and its reverse lookup zone ip6.arpa is mapped to this long record. So lots of ones and zeros here, and at the end we've got this .ip6.arpa. And the second part of this process is PTR record. PTR records in the reverse lookup zone map IPv6 addresses to host names. Now, reverse lookup zones, reverse lookups are essential for troubleshooting and verifying device identities in IPv6 networks. IPv6 offers two primary methods for address assignments, as you remember. It's DHCP version 6 and SLAC, or Stateless Address Autoconfiguration. And understanding the difference between these methods helps you choose the right approach for your network. Let's review the first one, SLAC. SLAC devices generate their own IPv6 addresses using the router's prefix and their interface identifier. It does not provide additional configuration options like DNS server addresses, while DHCP version 6 assigns IPv6 addresses and other parameters, for instance DNS servers, to clients. These are ideal for enterprise environments requiring centralized control. And we've also got this combined approach where we can use SLAC for address assignment and DHCP version 6 for additional parameters like DNS. Many organizations use a hybrid approach to balance simplicity and centralized management. Okay, congratulations, you've now learned how to configure DHCP version 6 and DNS in Windows Server operating system to support IPv6 environments. These skills are essential for managing modern networks and ensuring smooth communication between IPv6 enabled devices. Next up, we'll have the hands-on demo on how to implement or configure IPv6 scope in DHCP and Quad A records in DNS. So I'll see you there. Welcome to this hands-on demo where we'll configure an IPv6 scope in a DHCP server and create an Quad A record in DNS using your virtual lab infrastructure. This exercise will help you understand how IPv6 nodes dynamically register their addresses with DNS and how to manually configure Quad A record for specific hosts. As you remember, I'm working in my lab within the learnedlessons.com domain on an internal .2.0/24 network. The core components include domain controller, DHCP server, and member server, as well as router, gateway, IPs server. For now, I've just turned on two servers, that is lead DC1 and lead SVR1. So by the end of this lesson or this demo, you'll know how to configure IPv6 scopes in DHCP, create Quad A records in DNS, and verify name resolution for IPv6 addresses successfully. So let's get started. Let me connect to lead SVR1 server here, and I'll provide my domain net bias name, that is lead administrator, and my password, which is somepath1. Now on this server, in server manager, let's check if we've got DHCP server installed here. Seems like we don't, so let's install DHCP role really fast. I'll click Add Roles and Features, click Next, and select DHCP server here. Click Add Features here, click Next, Next again, Next, Install. Now when it's installed, I'll click Close here, go to Tools here, and by the way, let's double check these notifications here. So we'll need to complete DHCP configuration first before launching our DHCP server. So I'll click Next here. We'll be using the following user's credentials, lead/administrator, and I'll click Commit. So as you can see, creating security groups done, authorization DHCP server done. Click Close, go to Tools, find DHCP here, and launch it. That'll launch our DHCP server console, so we can continue. Now in the DHCP server console, I'll expand this learnedlessons.com, click on IPv6, and you can either right-click IPv6 or go to Action and select New Scope here. Here in this Welcome to the New Scope wizard, I'll click Next, and let's give it a name. For instance, for this particular demo, I'll name it Lead Headquarters IP version 6. We can also add a description here. For instance, IP version 6 scope for lead domain infrastructure. We'll click Next here, and let's add a prefix here. As you can see, and enter the IP version 6 prefix for addresses that the scope distributes and preference value for the scope. So let's add the following prefix: fd00:quad0 here, :quad0 once more, :0001, prefix length 64 and we'll click Next. Now, just like IP version 4, we need to exclude certain addresses from automatic assignment. We can, for instance, reserve the first 256 addresses for static assignments to servers and network devices. So let's go ahead and start. IPv6 address will be fd00. So fd00, the first part is already here, :0:0:1, and we'll add :quad0 here, once more, :quad0, and once more, :quad0, :0001. And IP version 6 address will add :quad0, :quad0, and once more, :00FF. We'll click Add here. The IP address range given is not valid. Okay, as you can see, we've encountered a common error when configuring IPv6 exclusions. That is, the IP address range given is not valid. This error occurs because there is an issue with the IPv6 address format or range logic. As you can see here, in this first part, we've got one format, and we've typed the other part in another format. So IPv6 addresses must follow exact formatting rules. Let's try retyping this in another format. Let's type fd 00:0:0:1 :1. And let me copy this address here and insert it here. And instead of : 1, we'll type : FF. Let's try adding this format. Okay, we got IP address range given is not valid once more. Let's try third format here. We'll type fd 00:0. And here we'll type fd 00:FF. We'll add it. The IP address range given is not valid. So that is for demonstration purposes, for you to know that it's quite important to keep the consistency in format. As you can see, we've got this after this one colon. So let's add one more colon and add one here. And here we'll add one more colon and add FF. Click add again, and now we've got this exclusion address range added. Now let me remind you here that this first part fd00, here this fd, it's unique local address prefix, and it's first octet continuation, and it also contains a local flag which is 0. Then these two quad zeros or compressed zeros is global ID. Here we've chosen all zeros for simplicity. And this final part, which is 1 or 0001, it's subnet ID. Now, this first FD here, as I've said, it's unique local address prefix, identifies this is a unique local address or ULA. Think of ULA as the IPv6 equivalent for private IPv4 addresses like 192.168. So if it was global unicast address, then it'd start with 2000. That'll be internet routable like public IP version 4. If it started with FE80, that'd be local network only. And if it starts with FC00, it's private networks like 192.168. Okay, let's click next here. We'll click all the defaults here and click finish. Now we've got the scope, lead headquarters IP version 6, added to our DHCP version 6 server. Welcome back. In our previous demo, we've seen how to configure DHCP6 scope. In this example, we'll perform this action in our actual infrastructure, so I'll revert lit SVR server to our previous state here. So I'll apply this snapshot here, and I'll go ahead and revert lit DC1 to previous state. So I'll apply this snapshot here. And now I'll turn on 3 servers that'll be lit DC1, lit SVR1, and lit DHCP server. So let me double click lit DHCP server and connect after it's completely loaded. I'll enter my credentials, and first off, let's launch CMD prompt here and check for the current IP configuration on DHCP server. So I'll type ipconfig/all. So let's make it a bit larger. Let's make it font 336, expand it a bit. So what can we see from this configuration? As you can see, we've got node type here hybrid. IP routing enabled, Wins proxy enabled no, and there is no default gateway, as you can see here, so it can't reach other network segments. IP routing disabled, so it can't forward IPv6 router advertisements. So let's fix this DHCP server's network configuration first, as that'll prevent it from properly participating in our IPv6 network infrastructure. First, let's add default gateway. So let me clear the screen. I'll type clear or CLS here, and we'll use netsh command. So we'll type netsh interface IPv4 set address. In double quotes, we'll type Ethernet, then static 192.168.2.20, that is our IP address. Net mask will be 255.255.255.0, and gateway 192.168.168.2.1. We'll hit return here. Now let's reveal our routing information with route print. So here we've got this first line, that's our default route, and this line 192.168.2.0, that's our network route, local network route. As you can see, we are missing our IPv6 routes. So let's enable IPv6 forwarding first. Now, there are several considerations here when enabling IPv6 router in your infrastructure. The decision of where to enable IPv6 forwarding depends on your network architecture and which device should act as the IPv6 router. Let's see the difference and the recommended best approach for the infrastructure, in this case for my lab. So what are the IPv6 router functions? Let's recall them. It sends router advertisements or array, it provides default gateway, it routes between IPv6 networks and enables IPv6 forwarding, and it tells clients about DHCP version 6 availability. And in my case, I've got domain controller and DHCP servers in this lab environment. So DHCP server functions are as follows. It assigns IPv6 addresses from scope, provides IPv6 configuration options, manages IPv6 lease information, and does not need to route packets. So in my case, I can separate these roles between DHCP server and DC1 server. So based on my network configuration or architecture, it will be recommended to follow best practices. To, for example, get domain controller as IPv6 router and keep DHCP server as DHCP only on this lead DHCP server. So let me switch back to DC1. Let me connect to DC1 here and enable IPv6 forwarding on lead DC1. So I'll provide my credentials. So why this approach works best for this particular lab? This separation of roles follows network design best practices and is more realistic for enterprise environments. The advantages of separating these roles will be that clear role separation, router versus DHCP function, and it's better security approach because DC or domain controller controls routing decisions here. It'll mirror real-world setup, and it'll be easier for troubleshooting, single source of router advertisements. So let's go ahead and launch command prompt here. We'll type cmd, and we'll also make it larger. like so, and will enable IPv4 routing or forwarding, on lead DC1. That is, let's check its IP configuration. We'll type ipconfig, ipconfig, and its IP is .22. So let's clear the screen and type the following. Interface IPv6 set interface Ethernet advertise equals enabled. Hit return, okay. Now let's tell clients to use DHCP version 6 for addresses. So let's get back to this previous command. Network netsh interface IP version 6 set interface Ethernet. Let's remove this part here and we'll type managed address equals enabled. Okay. We can also tell clients to use DHCP version 6 for other config. Enable the other stateful configuration flag so clients can receive DNS servers and other options from DHCP version 6. So I'll find this previous command here and let's modify it a bit. So netsh interface IP version 6 set ls set interface Ethernet. Let's remove this managed address and type other stateful enabled. Okay? And we can now verify the configuration. We can type netsh interface IPv6 show interface Ethernet. Perfect. Now our IPv6 routed advisement configuration on lead DC is complete and configured, correctly configured. So as you can see from this output, advertisement enabled, it sends routed advertisements. Then this managed address configuration enabled, it tells clients to use DHCP version 6 for addresses. Then this option, other stateful configuration enabled, which tells clients to use DHCP version 6 for options. Then if we scroll down here, we'll get some more output, but we need this neighbor discovery enabled. It's good as well because it's basic IP version 6 functionality. And router discovery here. We can now discover other routers. So this is a perfect configuration for IPv6 DHCP version 6 stateful auto configurations. Our router, which is lead DC1, will now send the correct signals to clients. Now let's create a fresh IPv6 scope with optimal configuration settings for our lab environment. So let me expand lead DHCP1 server, go to IPv6, go to Actions, New Scope, click Next here. We'll name it lead-IP version 6-main-scope. And again, I'll add a description here. For instance, primary IP version 6 scope for learnedlessons.com domain infrastructure. We'll click Next. Again, we'll add a prefix here. Let's define scope prefix. So as you remember, the scope prefix defines the network portion of IPv6 addresses that will be assigned. We'll be using a unique local address or ULA prefix appropriate for internal lab networks. So we'll type FD 00 colon quad zeros here, colon quad zeros once more, 0001 colon. We'll leave the preference as default and click Next. Here let's add :1 and for IPv6 address :FF. Click Add, click Next. Let's make it 8 days here, 0 hours, 0 minutes. Okay, click Next. Activate scope now. Yes. We'll click Finish. And the scope is activated. no address leases yet. And if we go to the scope here and go to address leases, as I've said, it's empty. Let's check scope status. So if we go to action, we can see that we've got this deactivate option, meaning that the scope is activated. And by the way, we can launch Windows PowerShell from Server Manager. We can click Tools, Windows PowerShell, and type the following command: get-dhcp server scope. Sorry, not DHCP server, but DHCP server 6. Oops, I think like I've made a typo here. Let's add DHCP server version 6 scope. So we'll get our scope with its prefix here, and it's active. Now let's check the functionality of DHCP server version 6 on lit SVR1. So let me connect to lit SVR1 here. Again, I'll enter my credentials and open command prompt when I'm logged in. So here it is. And here let's first check the host name with the host name command. It's lit SVR1. And check current IPv6 configuration. So we'll type ipconfig/all. So here, as you can see, we've got lots of missing elements, such as we've got no IPv6 address from DHCP scope, no link, only link local IPv6 address, no IPv6 lease information, no DHCP version 6 server address shown, and DHCP version 6 grid present but unused. So this presence of DHCP version 6 client grid means that the client is prepared for IPv6 DHCP, but the absence of any lease information means it's not successfully communicating with the DHCP server. So first let's try to clear the screen first and then try to run the following command: ipconfig-release 6. Hit return, and then instead of release we'll type renew 6, and we get an error occurred while renewing interface Ethernet. So let's run some specific diagnostics on this lit SVR1 server to confirm our diagnosis and gather more information about the network state here. First off, let's run the following: net sh interface IP version 6 show route. Hit return, and the following command was not found, and that's because I made a typo here: interface. Okay, we've got our route. So as you can see, it's missing some critical routes, such as DHCP scope network route and default IP version 6 route. Let's clear the screen again. Okay, let's switch to lit DHCP1 server and see what we can check. So I'll go to lit DHCP1 server here. Here we've got our lease. And one more thing we need to do, don't forget about this step. It's very important to assign a static IP address to the DHCP server. So I'll go to Server Manager, go to Ethernet here, double click it here, click Properties, go to Internet Protocol version 6, and as you can see, now it's obtaining an IP version 6 address automatically. So let's set it to use its own static IP address. So I'll type fd00:0:0:1:20 for our IP address, static IPv6 address. Subnet prefix length 64, and let's specify default gateway, for instance FD, like in my lab, fd00:0:0:1:1. And let's specify our preferred DNS server. That'll be our domain controller. By the way, I'll need to set up a static IP version 6 address on domain control as well. So that'll be fd, fd0, one more 0, colon 0, colon 0, colon, colon 1, double colon 22. Let's save this sentence and get back to our latest VR1 to double check if we can get appropriate IP version 6 address. So let's again run ipconfig release 6 and ipconfig renew 6. Now we get an IP version 6 address. Here it is. And if we switch to our lit DC1, go to tools, go to DNS, go to forward lookup zones, expanded, go to learnedlessons.com. As you can see, we've got our DHCP server 1 IP version 6 address and lit SVR1 IP version 6 address. Now we can also create a new quad A record. So for this we'll need to click on learnedlessons.com, right click on it or click action and go to new host A or quad A and specify the needed information. For instance, we want to create a quad A record for some web app, so we'll type web app, and here we'll need to specify our IP version 6 address. I won't be typing it in here because I haven't got any web app server, but that's for your information how to create new quad A record. I'll click cancel here. Okay, that's how you configure your DHCP version 6 server and how you troubleshoot different issues related to this process. That'll conclude our demonstration. I hope it was informative and I'd like to thank you for viewing. Welcome to this lesson on node types in IPv6. When planning an IPv6 network, it's essential to understand the capabilities of devices or nodes on your network. Classifying nodes helps define their roles and ensures proper configuration for communication and tunneling. And understanding node types is especially important when implementing tunneling technologies, as certain tunnels require specific node configurations. By the end of this lesson, you'll know how to classify nodes based on their IP capabilities and understand the implications for coexistence between IPv4 and IPv6. So let's get started. Okay, let's explore the different types of nodes that can exist in a network. First off, IPv4 only node. It supports only IP version 4 and is configured with an IPv4 address. It cannot communicate with IPv6 only nodes. This type of node is common in legacy systems and applications. Then we've got IPv6 only node. It supports only IP version 6 and is configured with an IP version 6 address. It operates in environments where all other nodes and applications use IPv6 exclusively, and it's ideal for modern IPv6 native networks. We also got this dual state node or dual stack node. It's IPv6/IPv4. These types of nodes support both IP version 4 and IP version 6 simultaneously. And this type of node is configured with both IPv4 and IPv6 addresses. They are used in most modern operating systems, including Windows Server 2008 and later, and Windows Vista and later. There is also IPv4 node. It's configured with an IP version 4 address, but may also support IP version 6. For instance, dual stack nodes. This term is often used interchangeably with IP version 4 only nodes. And IP version 6 node is configured with an IP version 6 address, but may also support version 4, and it's also dual stack nodes. This term is also often used interchangeably with IPv6 only nodes. Most organizations use dual stack nodes to ensure compatibility between IP version 4 and IP version 6 during the transition phase. Now some words about coexistence between IPv4 and IPv6. Since many applications and devices still rely on IPv4, most organizations deploy a coexistence strategy rather than fully transitioning to IPv6. This allows IPv4 only and IPv6 only nodes to communicate seamlessly. There are two common architectures for coexistence, and they are as follows: dual IP layer architecture and dual stack architecture. As for dual IP layer architecture, it was introduced in Windows Vista and still is used in Windows 16 and above versions and Windows 10 and later. It combines IP version 4 and IP version 6 layers with a single implementation of transport protocols like TCP and UDP. It simplifies migration to IP version 6 by reducing the number of files to maintain. And there is also dual stack architecture. It's used in Windows XP and Windows Server 2003, and it maintains separate protocol stacks for IP version 4 and IP version 6, each with its own implementation of transport protocols. It requires additional maintenance but provides clear separation between IP version 4 and IP version 6. So dual IP layer architecture is preferred for modern networks due to its simplicity and efficiency. Now, DNS plays a critical role in supporting IP version 6 networks. When adding IPv6 to your network, you must ensure that DNS is configured to handle both IPv4 and IPv6 records. The required DNS records for your infrastructure will be as follows. Host A resource record is used for IPv4 nodes. It maps host names to IPv4 addresses. While Quad A resource records are used in IPv6 nodes. They map host names to IPv6 addresses and typically register dynamically by IPv6 nodes. You'll also need reverse lookup pointer resource records, which maps IPv4 to IPv6 addresses back to host names to reverse DNS lookups. Now, when a host name resolves to both IPv4 and IPv6 addresses, the client chooses which address to use based on prefix policies. Now, Windows Server uses prefix policies to determine which IP address to prioritize when multiple options are available. Each prefix has a precedence level assigned to it, with higher precedence being preferred. The typical prefix policies are as follows. For IPv6 loopback address, the precedence is 50. For default gateway, IPv6 default gateway, the precedence is 40. For IPv4 compatible address, the prefix is 10. 6 to 4 tunelim, the prefix is 7. To radio, the prefix is 5, and so on. You can see this table on my screen. Now you can view prefix policies in Windows Server using the PowerShell commandlet. You type get net prefix policy. Let's review this coexistence practical example, and walk through this IPv4 and IPv6 coexistence. In this example, you can use Windows Server 2016 and above versions 19, 22, 25, where this Windows Server machine is configured with both IPv4, for instance 192.168.1.10, and IPv6, for instance 20.1:DB8:1 addresses. So that'll be our target server, and you can use a client machine that could be Windows 10 and above versions, so Windows 11 is preferred, of course. So here a client queries the DNS server for the host name. First step is DNS query here. Then the DNS server returns both IPv4 and IPv6 addresses. And the client here uses prefix policies to decide whether to use IPv4 or IPv6 address. There is also a fallback mechanism. If the IPv6 connection fails, the client falls back to IPv4. Now, modern browsers and applications often prefer IPv6 over IPv4 due to high precedence in prefix policies. Okay, great job. You've now learned about the different types of nodes in IPv6, how they coexist with IPv4, and the DNS infrastructure requirements for supporting both protocols. These concepts are essential for designing and managing networks during the transition from IPv4 to IPv6. Welcome back to this lesson on planning for a native IPv6 environment. As organizations transition from IPv4 to IPv6, some may choose to fully embrace IPv6 by eliminating IPv4 entirely. This approach is known as a native IPv6 environment, where all devices, applications, and network components operate exclusively using IPv6. Now, while a native IPv6 environment offers numerous benefits, such as improved scalability and simplified addressing, it requires careful planning to ensure compatibility across all systems. In this lesson, we'll explore the key considerations for planning a native IPv6 environment, including operating system support, router and firewall compatibilities, application readiness, and tunneling technologies. So let's get started. And we'll start with operating system support. One of the first considerations when planning a native IPv6 environment is operating system support. Modern operating systems like Windows Vista Plus and Windows Server 2008 Plus or above versions and their successors fully support IPv6. This includes Windows 10, Windows Server 2016, 19, 22, and 25, which are designed to work seamlessly in native IPv6 environments. Legacy systems, however, may lack full IPv6 support or require updates to function correctly. Before migrating to a native IPv6 environment, verify that all devices in your organization are running operating systems that fully support IPv6. The next consideration is router and firewall support. Another critical consideration here is router and firewall support. To ensure smooth operation in a native IPv6 environment, routers must be capable of handling IPv6 traffic natively, and firewalls should be able to detect and mitigate threats over IPv6 just as they do for IPv4. Now, many modern firewalls offer dual stack support, allowing them to handle both IPv6 and IPv4 traffic during the transition phase. Organizations should audit their networking hardware to confirm IPv6 compatibility and upgrade any outdated devices. Now, network devices such as printers, scanners, and cameras must also support IPv6. These devices often rely on embedded software that may not yet be IPv6 ready. Key points to consider here is to verify that firmware updates are available to enable IPv6 support and replace legacy devices that cannot be upgraded. Ensuring IPv6 compatibility across all network devices minimizes disruptions during the migration process. Another key consideration is application product support. applications play a vital role in determining whether an organization can adopt a native IPv6 environment. Some applications support IPv6 but require IPv4 to remain enabled. For example, Microsoft Exchange Server 2013 supports IPv6 only when IPv4 is also configured. Custom-developed applications may need code modifications to work as a native IPv6 environment. So conduct thorough testing of all applications to identify dependencies on IPv4 and address them before migrating. Now, custom applications developed within an organization must be designed with IPv6 in mind. Developers should ensure that code bases use IPv6 compatible APIs, and testing accounts for IPv6 specific scenarios such as larger address spaces and different header structures. So transitioning custom applications to IPv6 often involves updating libraries and protocols to align with IPv6 standards. Now some words about IPv6 tunneling technologies. So during the transition from IPv4 to IPv6, tunneling technologies are often used to encapsulate IPv6 packets within IPv4 headers. This allows IPv6 traffic to traverse IPv4 only infrastructure. And let's see how it works. First, the IPv4 protocol field is set to 41 to indicate an encapsulated IPv6 packet. And then the source and destination fields in the IPv4 header specify the tunnel endpoints. Now, tunneling does not establish secure connections automatically, so additional measures may be needed to protect tunnel traffic. Now, common tunneling technologies include as follows: ISATAP, it's infra-site automatic tunneling addressing protocol for internal networks. Then 624 for connecting IPv6 sites over NAT or IPv4 networks, and Teredo for traversing NAT devices. Now, to better understand tunneling, let's look at some real-world examples. For instance, remote procedure call or IRPC over HTTP, used by Outlook Anywhere to send email data securely over the internet. It's similar to how IPv6 packets are encapsulated within IPv4 headers. Or another example is virtual private networks or VPNs. They encapsulate private network traffic within public IP packets. So it demonstrates the concept of embedding one protocol inside another. Now, tunneling is a versatile technique used in many networking scenarios beyond IPv6 migration. Okay, congratulations, you've now learned about the key considerations for planning a native IPv6 environment, including operating system, router, firewall, and application support. You've also explored the concept of IPv6 tunneling and its role in facilitating the transition from IPv4 to IPv6. Welcome back to this lesson on ISATAP or Intra-Site Automatic Tunnel Addressing Protocol. It's a key component, key technology for transitioning from IPv4 to IPv6. ISATAP enables IPv6 communication over an existing IPv4 infrastructure by tunneling IPv6 packets inside IPv4 packets. So ISATAP is designed for use within private networks and cannot be used over the internet. It's particularly useful for connecting IPv4 only subnets with IPv6 only subnets during the transition phase. So in this lesson we'll explore how ISATAP works, its address format, the role of an ISATAP router, and how to configure it. So let's begin. How ISATAP works. ISATAP is an address assignment technology that provides unicast IPv6 connectivity between IPv6 and IPv4 hosts over an IPv4 intranet. Here is how it works. First, tunneling IPv6 in IPv4. So here, IPv6 packets are encapsulated inside IPv4 packets for transmission across the network. This allows IPv6 hosts to communicate even when the underlying network infrastructure is IPv4 only. Then direct communication. Here, two ISATEP hosts on an IPv4 network can communicate directly without requiring an ISATEP router. Then communication or through an ISATEP router. If one network has only IPv6 only hosts, an IPTAP router acts as an intermediary, unpacking IPv6 packets and forwarding them to the IPv6 only network. So all ISATEP nodes are part of the same IPv6 network or subnet, making them appear as if they are on the same logical network. Now let's take a look at ISATEP address format. So ISATEP addresses are created using a combination of a 64-bit unicast prefix and the IPv4 address of the host. The format depends on whether the IPv4 address is private or public. So for private IPv4 address, there will be 64-bit unicast prefix first, and for public IPv4 address, there will be 64-bit unicast prefix, for example, 2001:db8 200 and so on. And by the way, there should be 5 EFE identifier in the address, which will signal that it's an ISATEP address. So if you see this 5 EFE identifier, it signals that it's an ISATEP address. Now, what's an ISATEP router? An ISATEP router plays a critical role in enabling communication between IPv4 and IPv6 networks. Its responsibilities are as follows. First off, advertising the IPv6 prefix. The ISATEP router advertises the IPv6 prefix that ISATEP clients use to configure their addresses, then encapsulating and decapsulating packets. So here, when applications send data through an ISATEP interface, the IPv6 packet is encapsulated in an IPv4 packet and delivered to the destination ISATEP host. For IPv6 only networks, the ISATEP router unpacks IPv6 packets and forwards them to the IPv6 only hosts. So using an ISATEP router ensures seamless communication between IPv4 and IPv6 hosts during the transition phase. Now, how do we configure ISATEP? Configuring ISATEP is straightforward thanks to the auto-configuration mechanisms built into modern Windows operating systems. So automatic configuration, here ISATEP hosts automatically create ISATEP addresses if they can resolve the name ISATEP on the network. By default, the ISATEP component is enabled in Windows 8.1 and later versions, and Windows Server 2016 and later versions. We can also enable ISATEP tunneling. The simplest way to enable ISATEP is to configure an ISATEP host record in DNS that resolves the IPv4 address of the ISATEP router. Once configured, all Windows hosts can resolve the ISATEP name will begin using a specific ISATEP router. Now, avoid configuring ISATEP manually via host files, as it's difficult to manage at scale. Now, by default, DNS servers on Windows Server 2008 and later versions block ISATEP resolution due to the global query block list. To use an ISATEP host, you must remove ISATEP from this block list. So you'll need to open PowerShell with administrative privileges and run the following command: remove DNS global query block list entry ISA-tab. This step is essential for ensuring that DNS can resolve the ISA-tab name correctly. Now, there are also alternative methods for configuring ISA-tab. If DNS configuration isn't feasible, you can configure ISA-tab using alternative methods. You can use PowerShell with set net ISA-tab configuration router property command. You can use netsh command with netsh interface IPv6 ISA-tab set router, or you could use group policy, configure the ISA-tab router name group policy setting to specify the ISA-tab router. So these methods are useful for environments where DNS-based resolution isn't practical. There are also limitations of ISA-tab. While ISA-tab is a valuable tool for transitioning to IPv6, it has some limitations, such as single subnet constraint. All ISA-tab nodes belong to the same IPv6 network or subnet, which may not align with your Active Directory site structure, or not suitable for large deployments. ISA-tab is best suited for limited testing and small-scale deployments. For enterprise-wide adoption, native IPv6 support is recommended. Now, you can use ISA-tab as a temporary solution during the transition phase, not as a long-term strategy. Okay, great, you've now learned about ISA-tab, including how it works, its address format, the role of an ISA-tab router, and how to configure it. These skills are essential for bridging IPv4 and IPv6 networks during the transition phase. Welcome back to this lesson on 624, a tunneling technology designed to provide IPv6 connectivity over the IPv4 Internet. It's another key technology in our list to transition from IPv4 to IPv6. As organizations transition from IPv4 to IPv6, technologies like 624 play a vital role in bridging the gap between the two protocols. So 624 is specifically intended for IPv6 communication over the public IPv4 Internet and is not suitable for internal networks or scenarios involving network address translation. In this lesson, we'll explore how 624 works, its address format, configuration options, and limitations. So let's dive in. And we'll start from understanding 624 mechanism. 624 is a tunneling mechanism that enables IPv6 traffic to traverse the IPv4 Internet. It allows IPv6 sites where two IPv6 only sites to communicate over an IPv4 only infrastructure, and it allows IPv6 hosts where individual IPv6 hosts to connect to IPv6 networks via the IPv4 Internet. So the 624 name reflects its purpose, facilitating IPv6 communication over IPv4 networks. However, 624 has a significant limitation. It cannot work with NAT devices. This is because NAT modifies IP headers, disrupting the encapsulation process used by 624 technology. Now, how 624 works? The core of 624 lies in its use of a 624 router, which acts as a gateway between the IPv6 and IPv4 worlds. The components are as follows. External interface. The router's external interface is assigned a public IPv4 address. This address is used to encapsulate IPv6 packets for transition over the IPv4 Internet. Another component is internal interface. The router's internal interface is assigned to 624 IPv6 address. This address is advertised to client computers within the site. And finally, client configurations. Here, client computers automatically configure themselves as 624 hosts by using the advertised 624 network address. These hosts send IPv6 traffic to the 624 router, which forwards it over the IPv4 internet. Now, the 624 router ensures seamless communication between IPv6 only hosts and networks across the IPv4 internet. Now let's take a look at 624 address format. The IPv6 address used in 624 is derived from the router's public IPv4 address. And the format is as follows: 2002, and then the first part, and then subnet ID, interface ID. So here 2002 indicates that the address is part of the 624 range. Then this part www.xxyyyzz represents the colon hexadecimal version of the router's public IPv4 address. Then subnet ID allows for subnetting within the 624 networks, and interface ID identifies the specific device. Now, if the router's public IPv4 address is 192.168.1.1, the corresponding 624 prefix would be 2002 C08800101:/48. So you can see this example on my screen. Here is IPv4 address and here is 624 address. Now, configuring 624 depends on whether the computer has a private or public IPv4 address. If it's a private IP address, if the computer is behind a NAT device, the operating system assumes it cannot use 624. The media state of the 624 tunnel adapter will show as disconnected. If the computer has a public IP address, the operating system enables the 624 tunnel adapter, and we can use the ipconfig/all command to verify the status of the 624 tunnel adapter. Now, always ensure that NAT is not present when deploying 624, as it disrupts the tunneling process. How do we enable 624 router functionality? So, Windows Server 2016 and later versions can be configured as 624 router using several methods. The first method is internet connection sharing. We can enable ICS to automatically configure the server as 624 router, or we can use Windows PowerShell with get net 624 configuration, which displays the current 624 configuration, set net 624 configuration, which modifies the 624 settings, and reset net 624 configuration that will reset the 624 configuration to its default state. Then we can use netsh command. Here we can use netsh to create and configure 624 routers, relays, and interfaces. So PowerShell and netsh provide granular control over 624 configurations, making them ideal for advanced deployments. Now, there are also limitations of 624. While 624 is a valuable tool for IPv6 adoption, it has some limitations. First off, NAT incompatibility. 624 does not work with NAT devices as they modify IP headers and disrupt encapsulation. Second, performance issues. Encapsulation introduces overhead, potentially impacting performance. And third, deprecation trends. 624 is considered outdated in many modern networks due to reliability concerns and the rise of native IPv6 support. So organizations are increasingly moving away from 624 in favor of native IPv6 deployments or other tunneling technologies like Teredo. Okay, great job. You've now learned about 624, including its purpose, how it works, its address format, and how to configure it. While 624 is a useful transitional technology, it's important to recognize its limitations, especially in NAT environment. Welcome to this lesson on Teredo, a tunneling technology that enables IPv6 communication over IPv4 Internet, even when NAT or network address translation is in use. So Teredo is particularly useful for hosts behind NAT devices, as it allows them to communicate with IPv6 networks despite the limitations imposed by NAT. While similar to 624, Teredo is specifically designed to work in environments with NAT where NAT is present, making it a critical tool for IPv6 adoption in NAT-heavy networks. So in this lesson, we'll explore how Teredo works, the address structure, and how to configure it. Let's start. And we start with how Teredo works. Teredo facilitates IPv6 communication between two Teredo clients over the IPv4 internet by using a Teredo server as an intermediary. So here how it works. First, Teredo initiates communication. Both Teredo clients initiate outbound connections to the Teredo server. This outbound communication bypasses the restrictions imposed by NAT devices, which typically block unsolicited inbound traffic. Second step, direct communication. Once the connection is established through the Teredo server, further communication occurs directly between the two Teredo clients. And third, Teredo relay. Teredo can also facilitate communication with IPv6 only hosts on the IPv6 internet by using a Teredo relay, which forwards packets between Teredo clients and the IPv6 internet. Now, Windows operating systems default to using the Microsoft-provided Teredo server, which is at teredo.ipv6.microsoft.com. Let's take a look at Teredo address structure. So a Teredo address is a 128-bit IPv6 address with a unique structure that includes information about the Teredo server and the client's NAT configuration. So here, Teredo specific prefix is 32 bits prefix. It always starts with 2002, identifying it is a Teredo address. So Teredo server IPv4 address is 32 bits and it identifies the IPv4 address on the Teredo server. Options 16 bits contains flags and configuration options such as whether the client is behind NAT. And obscured external port 16 bits represents the external port used by the NAT device for communication obscured to prevent translation. And obscured external IP address, it's 62 bits. It represents the external IPv4 address of the NAT device, also obscured to prevent translation. So the obscuration of ports and IP addresses ensures compatibility with NAT devices, enabling seamless communication. Now, how do we configure Teredo? You can configure a computer running Windows Server 2016 and later versions as a Teredo client relay or server. So first, you use default configuration. By default, a computer is configured as a Teredo client. Teredo is disabled on domain networks unless the computer is explicitly configured as an enterprise client. We can also use Windows PowerShell here to configure it. We use set-net Teredo configuration command let to configure Teredo settings, and you can use the netsh command to specify custom Teredo servers instead of the default Microsoft server. Teredo is typically used only when a when other translation technologies like native IP6, 624, or ISOTAP is unavailable. Now, while Teredo is a powerful tool for IPv6 adoption, it has some limitations. First off, performance overhead. Tunneling introduces additional overhead which may impact performance. Then net dependency on net. Teredo relies on net behavior which can vary between devices and networks. And security concerns. Teredo traffic may bypass firewalls and security policies, posing potential risks. So use Teredo as a transitional solution rather than a long-term strategy for IPv6 deployment. Okay, that will conclude our lesson on Teredo. Now you've learned about Teredo, including how it works, its address structure, and how to configure it. These skills are essential for enabling IPv6 communication in net-heavy environments during the transition phase. Welcome back to this lesson on port proxy. It's a service that enables applications that do not support IPv6 to communicate with IPv6 hosts. Port proxy acts as a bridge between IPv4 and IPv6, translating incoming IPv6 packets into IPv4 and vice versa. So port proxy is particularly useful for legacy applications that rely on IPv4 specific APIs and cannot natively support IPv6. In this lesson, we'll explore how port proxy works, its limitations, and how to configure it. So let's dive in. Now, how port proxy works? Port proxy operates by translating network traffic between IPv4 and IPv6. And here we've got two parts. Translation process. Here, incoming IPv6 packets for an application are translated into IPv4 and passed to the application. Similarly, outgoing IPv4 packets from the application can be translated into IPv6. And the second part is proxy between IPv4 and IPv6 hosts. Here, port proxy can act as a proxy between IPv4 only and IPv6 only hosts. Now, DNS must be configured to resolve the remote host's name as the IPv4 address of the port proxy computer. So port proxy is often used in environments where tunneling technologies like Teredo or 624 are not feasible. Of course, there are some limitations of port proxy. While port proxy is a useful tool, it has also several limitations. And the first limitation is TCP-only support. Port proxy supports only TCP connections and cannot handle UDP traffic. The second limitation is application layer restrictions. It cannot modify address or port information embedded in the application layer data. So protocols like FTP, which embed address information in the data payload, is incompatible with port proxy. So for most scenarios, tunneling technologies are preferred over port proxy due to their broader compatibility. Now, how do we configure port proxy? You can configure port proxy on Windows Server 2016 and later versions using the netsh interface port proxy command. And here is the other steps to how you configure it. First, you open command prompt with administrative privileges. Then you add a port proxy rule with netsh interface port proxy command, and then you verify the configuration with netsh interface port proxy show all command. So proper DNS configuration is critical for port proxy to function correctly, especially when acting as a proxy between IPv4 and IPv6 hosts. Welcome back to this lesson on transitioning to IPv6 only networks. So as organizations move toward adopting IPv6, careful planning is required to ensure a smooth migration. While the ultimate goal is to achieve an IPv6 only environments, The transition process involves multiple steps and extended coexistence with IPv4. The transition to IPv6 is a gradual process that requires upgrading applications, infrastructure, and devices to support IPv6 while maintaining compatibility with IPv4. In this lesson, we'll explore the steps involved in transitioning to an IPv6-only network and the considerations for each phase, so let's get started. And here the first step in transitioning to IPv6 is upgrading applications to be IP version independent. Modern APIs use the support both IPv4 and IPv6, leaving the choice of IP version to the operating system. As for legacy applications, all the applications that rely on IPv4 specific APIs must be upgraded to use newer APIs that support both protocols. Then we upgrade routing infrastructure. To support native IPv6 routing, organizations must upgrade their routing infrastructure. Native IPv6 routing the routers must be upgraded to support both native IPv6 routing and IPv6 routing protocols. And during the transition phase, routers should support both IPv4 and IPv6 to ensure seamless communication. Then we upgrade devices. Not all devices support IPv6 out of the box. Organizations must verify and upgrade devices to ensure compatibility. Most modern networking hardware supports IPv6. Not all the devices may require firmware, but all the devices may require firmware upgrades and updates or replacement. Devices like printers, scanners, and IoT devices must also support IPv6. So failing to upgrade peripheral devices can create bottlenecks in an otherwise IPv6 ready network. Then we upgrade DNS infrastructure. So DNS plays a critical role in IPv6 adoption, and to support IPv6, organizations must update their DNS infrastructure. Add Quad A records for IPv6 addresses and PTR records in the ip6.arpa reverse domain, and ensure DNS service supports DNS traffic over IPv6 and dynamic updates for IPv6 resource records. Then transition strategies. Most organizations adopt a coexistence strategy during the transition phase. So here, dual stack approach and removing IPv4 approach are in play. So hosts are upgraded to support both IPv6 and IPv4, allowing access to both types of resources, and IPv4 should only be removed after all dependent resources are upgraded or replaced with IPv6 equivalents. Okay, you've now learned the steps involved in transitioning to IPv6 only network, including upgrading applications, routing infrastructure, devices, and DNS. So these steps are essential for planning and executing a successful IPv6 migration. I hope it was informative, and I'd like to thank you for viewing.